So the calculations we did in the prior section is about ideal solutions, right? So again, these are solutions where the interaction we observe in the solution state is of the same strength as the interaction observed in the solute-solute and the solvent-solvent interaction, okay? So in other words, ideal solutions are solutions where the delta H of solution is pretty close to zero or is equal to zero, okay? There's never one that's exactly zero, but we can approach ideality. Now, again, why are we necessarily concerned by ideal solution? Because the calculations are a lot easier when we have ideal solutions versus non-ideal solution. You might remember the same concept was used when we're discussing ideal gas versus real gas, right? Now, the difference between ideal solution and what we refer to as non-ideal, or you can call it real solutions, is that in non-ideal solution, the delta H of solution is not zero. So it could be positive or it could be negative. So when it's positive, we call it an endothermic solution. And when it's negative, we call it an exothermic solution. This is actually not new. I had discussed this maybe a couple of sections ago when I first talk about how to break apart the components of the delta H of solutions. Okay, and so as a reminder, an endothermic solution will be one where the mixing term, the delta H of mix, is actually weaker compared to the delta H of solute and solvent. So in other words, when you mix the two things together, the interaction between the solute and the solvent is weaker than you observe when the two things are separate. Now, because they're weaker, they don't really want to interact with each other, right? So solute would want to interact with the solvent would want to interact with the solvent, but the solute and the solvent don't want to interact with each other. So as a result, they're kind of repelling each other. When they repel each other, then the likelihood that they would go into the gas phase is higher. So then there is more vapor than you expect compared to ideal solution. So for an endothermic solution, you will see that your P vap of this endothermic solution is going to be higher than your vapor pressure that you observe in the ideal solution. When an exothermic solution is the opposite. In the exothermic solution, the solute and the solvent have stronger interaction compared to solute and solvent. So because they have stronger interaction, they're kind of stuck in the liquid phase. They're really interacting strongly with each other, which means that few of them will be able to escape. And so in the case of an exothermic solution, the P vap of the exothermic solution is going to be less than the vapor pressure we calculate in the ideal solution, which is the one in Raoult's law. Okay, so we can plot this out here, keeping in mind again that the Raoult's law pressure total is given by this expression, right, which is the mole fraction of solvent times the vapor pressure of solvent, mole fraction of solute times the vapor pressure of solute. So I'm going to explain these three graphs right here. The explanation is given in your lecture notes as well. But we're going to take a look at plot A. Plot A is for the ideal solution. So here, both A and B, the two components in the solution, are both volatile. So if we're just looking at the partial pressure of component A. Okay, so partial pressure of component A is going to be given by the mole fraction of A. So the higher the mole fraction, the higher the partial pressure of A, right? So eventually it reaches a maximum here, which is at this point right here for the red line. And that's when all you have is A. That number would equal to the pressure of pure A, okay? As you start adding B, which is this blue line right here, so B number is 0 right here, but then it goes to 1, mole fraction of 1. So at that point, all you have just B, so then the pressure is going to be just the vapor pressure of pure B. Now, what happens when you mix the two things together? Well, you might imagine that vapor pressure of the solution is going to be mole fraction of A times the vapor pressure of pure A, and then the mole fraction of B times the vapor pressure of pure B. And that's exactly what this purple line is showing. It starts with A being 1, but then as you add B, slowly the B component is going to add to that number. So then you get this blue line that eventually becomes equal to pure B when there's no A around, right? But that purple line that I just had there is basically the line that corresponds to Raoult's law, okay? So that's for an ideal. Now, what happens when you have a deviation? Well, it depends on the kind of deviation you have. So if you're having the exothermic type of deviation, the non-ideal solution that's exothermic, remember that means the strength of interaction in the mix, right? When solvent and solute are combined, is stronger. That pulls down the molecule, stay in the liquid state, so the vapor pressure is going to be lower. So here again, this dotted line now corresponds to the ideal vapor pressure. So that's the ideal line. The actual vapor pressure is going to be lower, shown by that purple curve, right? So it's going to be less than the ideal vapor pressure. So if you do your experiment and you make a calculation of the ideal vapor pressure and you see that your experimental vapor pressure is actually less than that number, then you know you're dealing with an exothermic type solution, which has very strong solid-solvent interaction. If you have an endothermic type solution where the solid-solvent interaction is weaker than what you expect from the ideal interaction, then you get the opposite behavior. So again, here this straight line is your ideal vapor pressure, and then the purple curve corresponds to the actual vapor pressure that you will observe for an endothermic solution, because it's going to be higher, because again, the solid and the solvent would try to avoid each other and they would escape to the gas phase. That's really the explanation there in those three parts. Now we're going to take a look at an example to help us analyze what kind of non-ideal solution we're dealing with. So here we were told that we have a solution containing some mass of chloroform, gives us a formula there, and then some mass of acetone also gives us the formula. The vapor pressure of pure acetone and pure chloroform are also given, and what we have to do is first calculate the ideal total vapor pressure. So again, assuming the solutions are ideal, what would that total vapor pressure be? That's just using Raoult's law. And then we were told that the experimentally measured vapor pressure is 312 torr. Is this solution's ideal or not? If it's not ideal, what kind of interaction happened between acetone and chloroform? Is it stronger or weak? Okay, so in other words, is it going to be endothermic or exothermic is what we're being asked. All right, so let's take a look again at the right side where we're going to do our calculation. So ideal behavior, as I said earlier, it just means that your solution calculations will follow Raoult's law, because that's what Raoult's law applies, right? So Raoult's law, of course, that pressure total can be calculated by taking the mole fraction of A times the vapor pressure of pure A plus the mole fraction of B times the vapor pressure of pure B. So I'm going to need to calculate mole fraction, which means I'm going to need number of moles. So here's calculating the number of moles for chloroform, one of the components. And then here I calculated the number of moles of acetone, which is the other component. And then in the second step, I calculated the mole fraction of chloroform, just the number of moles of chloroform divided by the total, and that's 0.176. And then for acetone, it's as simple as taking 1 minus the other number, which is 0.824, but here I calculated by using the number of moles divided by the total. Once I get the mole fraction, I can then use Raoult's law to calculate my ideal vapor pressure total. This is the mole fraction of chloroform multiplied by its vapor pressure in the pure state. This is the mole fraction of acetone multiplied by its vapor pressure in the pure state, giving me 325 torr. So this is my P ideal, okay, because I calculated using Raoult's law. In the question, I was told that experimentally measured vapor pressure is 312 torr. So that means that is less than my ideal vapor pressure. So if the interaction has less pressure compared to ideal, that means that there's fewer particles that escape to the vapor state, right? So if there's fewer particles, that's that the interaction between solvent-solute is stronger than I expect, stronger than my ideal solution assumption, okay? So that, of course, means that my absolute value of my delta H mix is going to be stronger than the absolute value of the delta H of solvent plus delta H of solute. So this is an example of an exothermic solution.